Good morning, calculus students. So, Mr. Chen again. So, today I would like to talk about the logistic model of population growth. And this one is also the continuation of chapter 9 from the Rogowski Calculus BC textbook. And the model for the population's logistic growth, it's considered P of t. So that equals L all over 1 plus A times e to the power of negative kt. So for those you might be wondering, L, A, and K, we'll talk about that in a little bit. So it has the derivative of dp over dt, so trying to take the derivative, t is the variable. L, that's just a constant, so we'll talk about that L. It's called the population capacity or the carrying capacity. So capacity, that means it's like a maximum population, that the model can handle. And for K, it's always considered the proportional constant. And then P, definitely it's considered the population. So derivative, the rate of change of the populations, it's considered K times P times the quantity of 1 minus P over L. And then also A can be founded by using L minus P naught or P0, the initial population, all over P0, the initial population. So again, L is the population capacity or the carrying capacity. It's always the horizontal asymptote as t goes to infinity. So as you can see that for the graph right here, so it's always the graph goes like this one. It's kind of like a sideways shifted inverse tangent curve. So this one, I would like to put in that L right up here because that would be the limit, which is considered that the carrying capacity or the maximum population. And then obviously down the bottom, this one is just considered the x-axis, which is 0. Okay, so using the model to find out that the population's the original functions. So write the solution to the initial value problem with dp over dt equals 0.08 times p times the quantity of 1 minus p over 1000. So where p of 0, it's 100. And use it to find out the population when t equals 40 and when t equals 80. So one thing that you want to do here, compare and contrast. So we do know that the given rate of change, so dp over dt, so this one is 0.08 times p times 1 minus p over 1000. So you just want to compare to the model, the original, the general model, so it's k times p times 1 minus p over L. So you may be wondering L, which is considered 1000, so the maximum capacity, and then K, it's 0.08, the proportional constant. So one thing that we notice, so P equals 0 or P equals L if the derivative is 0. Okay, so we can just say that. So using the model, so we can just set up that P of t. So L, which is considered 1000, all over 1 plus A. Well, A, in order to get that, so it's L minus P0. So L, which is 1000. Initial population, it's considered 100. Okay, so 1000 minus 100. So L, maximum capacity, minus initial population, which is what? It's 100. And then divided by 100. So we got 900 over 100, which is 9. So 1 plus 9 times e to the power negative kt. So k, which is 0.08. So negative 0.08 times the time. So once we set up the model, we can just find out the population at t equals 40, t equals 80. So by plugging the numbers, so p of 40, and then p of 80. So definitely you can just put it into the calculator or just simply, do it manually. But normally this one is a calculated problem on the AP test. Because you don't want to round things up by the time you evaluate it, because that would be a lot of work, okay? So just plug in the time. And then the other one similar, so 1000. So 1 plus 9 times e to the power negative 0.08 times 80 to get the population. So here's another example for this. So the rate of change of the number of coyote in the population is given by dc over dt, 9c minus 3c squared. And where c is the number of thousand of coyote t year after January 1st, 2000. So find the value of c such that the number of coyote is increasing the fastest. Okay, so In order to create the model, so we need to set up that the differential equation with the factor form, which is similar to what we found from the original dp over dt. So we need to set up the factor form. This one is a non-factor form. So take out that 9c there. So we got 1 minus, this one will be c over 3. Because 9 over 3, then that would be 3. And then c times c, then that would be c squared. So it's 9c times the quantity of 1 minus c over 3. So compare and contrast. As you may notice that, so k, it's 9. And then c, just like p right there. And then L, the maximum capacity, then that would be 3. Okay, so got to be careful that the line out with the problem here. So set up that the populations model. So we do have C of t. So that equals L, which is 3, over 1 plus 9 times e to the power. For that k, so k, it's already, well, a, we don't know what that is yet, so a is not 9. Okay, we need to find out what that is. So this one looks like it's not given with the initial condition, so let's just say that a first. So a times e to the power of negative, well, we do know that k is 9, so negative 9t. Okay, so in order to solve for a, so a, which is considered L minus P0 divided by P0. Okay, so one thing that we notice, if this one is considered, okay, so this one, the population is growing the fastest, so that means it's P equals L over 2. So P equals L over 2, so what we found here is 3 over 2. So that means it's considered 1.5. And the unit for this one, it gotta be, okay, so this one, it shows that the number of coyote, so 1.5 thousands of coyote. Thousands of coyotes. Okay, so again, in order to find out what A is, so we can always using that the model, which is considered L minus P0 divided by P0. So L is 3. And this one is not given with the initial population. Oh, it doesn't even ask, okay, find the value of C such that the number of coyote, it's increasing the fastest. So if this one shows that the rate of change is growing the fastest, so that means the second derivative. Okay, so here's the statement. So the number of coyote, it's increasing the fastest. So that means the rate of change is considered the maximum. So we need to take the second derivative of this. Okay, so take the second derivative using that model. So we do have okay, so dc over dt for the second derivative. So again, c would be the population, so that would be 9. Okay, so 9 times c prime minus 6c times c prime. Okay, so this one, it's a little bit hectic because that's a lot more work need to be done. So that means this model, so this the second derivative would be considered 0 because that the rate of change would be the maximum. So take out c prime, or take out 3c prime. So we do have 3 minus 2c. Okay, so C prime, which is this model, the rate of change. And then we want to find out the populations. So plug in that C prime. So we got 0 equals 3 times 9 C minus 3C squared times 3 minus 2C. Okay, so one thing that we found is that this one would be considered 3 over 2. So we found it, which is 1.5. Okay, so this one, it could be either the fastest or the slowest. Okay, so we don't know. But let's find out the other one here as well. So the other one we can set equal to 0. So this one, 9C equals 3C squared. So this one is 3C squared minus 9C, so that equals 0. So take out that, the greatest common factor, so we do have 3C, and then C minus 3. So C could be 0 or C could be 3. So I would say that the number of coyote at the fastest rate increasing here, then that would be considered 3. 3 half. Okay, so according to the formula, it's L over 2, which is the point at which the population is growing the fastest. Okay, so it could be either 3 half, 1.5, or at 3. Okay, so this one you might want to do the second derivative. Just plug in a number back to the first derivative and find out what that is. So plug in that if that's the fastest rate of change. So dc over dt. So 9 times 3, then that would be 27. And then 1 minus 3 over 3, that's 1. So this one is 0. So this one would be the slowest rate of change. Is 0, there's no rate of change there. And then the other one, dc over dt. So you just plug in 3 half. So 9 times 3 over 2. So 1 minus 3 over 2 divided by 3. So this one will give you the fastest rate of change. So 27 over 2 times 3 over 2 divided by 3, then that would be 1 half. So 1 minus 1 half, 1 half. So 27 over 4. So this one, it's the number of coyote versus the time per year. Okay, so this one is the fastest rate of change. So I would say that the number of coyote, it's increasing the fastest, so that would be 3 over 2. This one, it shows the number of population at the slowest rate of change. Okay, so this one is the slowest. This one is the fastest. Okay, so that's it. Thank you for watching the video today. So in case I do have any questions, so please put it into the YouTube comment bar. So I'm more than happy to reply that. Okay, so I'll see you guys next time. Take care.